Imagine drifting through the quiet of space, beyond the reaches of our sun, beyond the planets and the asteroids, into the vast ocean of interstellar darkness. The further you go, the colder and lonelier it becomes. And then, somewhere in the void, you see it, a region so dark, so impossibly black, that it seems to swallow the very fabric of reality itself. A black hole. Black holes are among the most mysterious objects in the universe. They are born from the violent collapse of massive stars, places where gravity is so intense that nothing, not even light, can escape. They warp space and time in ways that defy human intuition, creating a cosmic abyss that challenges our deepest understanding of physics. But what exactly is a black hole? And what would happen if we ventured too close to one? The formation of a black hole. The journey of a black hole begins with the life and death of a giant star. Stars, much like our sun, burn for millions or even billions of years, fusing hydrogen into helium and producing immense energy. This energy pushes outward, balancing against the inward pull of gravity. But when a truly massive star reaches the end of its life, it runs out of fuel. The delicate balance is lost. Gravity wins. In the final moments of such a star, it collapses in on itself, forming an incredibly dense core. The collapse is so extreme that it creates what physicists call a singularity, an infinitely dense point where the laws of physics as we know them cease to function. Around this singularity, an invisible boundary forms, known as the event horizon. Once something crosses this boundary, it is lost forever, trapped by gravity's inescapable grip. This process is unimaginably violent, releasing more energy in a fraction of a second than our sun will emit in its entire lifetime. The dying star undergoes a supernova explosion, blasting its outer layers into space and leaving behind only its collapsed core, a black hole. Some black holes form in binary star systems, where a companion star may be gradually devoured by the black hole's immense gravitational pull. This leads to the creation of an accretion disk, a swirling mass of gas and dust spiraling around the event horizon at nearly the speed of light, emitting powerful X-rays detectable by astronomers. It is in this chaotic and extreme environment that we witness the final birth of a black hole. The event horizon, a one-way door to oblivion. The event horizon of a black hole is often described as the point of no return. It's a boundary in space where escape velocity, the speed required to break free from gravitational pull, exceeds the speed of light. Since nothing can travel faster than light, nothing that enters can ever leave. At first glance, the event horizon may seem like a solid surface, a kind of cosmic boundary, but it is not. It is an invisible, theoretical limit where the laws of physics begin to shift. If you were to approach the event horizon in a spaceship, you would see nothing unusual until it was too late. What would happen if you drifted toward a black hole? At first, nothing unusual might happen. In the emptiness of space, there are no physical barriers marking the event horizon. But as you get closer, something truly strange begins. If you were watching from a safe distance, you would see time itself slow down for the falling object. The closer it gets, the slower time appears to move. From your perspective, the object would never actually cross the event horizon. Instead, it would appear to freeze, growing ever dimmer as the light struggles to escape. From the perspective of the falling traveler, however, time would continue as normal. Yet they would experience an increasing gravitational gradient, stretching and warping their perception of space and time. They would pass through the event horizon unaware, their fate sealed. Spaghettification, the ultimate stretch. As you fall toward a black hole, the difference in gravitational pull between your feet and your head becomes extreme. If you're falling feet first, gravity at your feet is far stronger than at your head, stretching you out like a piece of spaghetti. Scientists call this spaghettification. It's an eerie and unsettling fate where you are torn apart atom by atom, pulled into the depths of the singularity. Even if an astronaut were in a heavily shielded spaceship, there is no known force that could withstand this process. The fabric of space-time itself distorts so dramatically that no material or biological form could endure it. To an observer watching from afar, the astronaut would appear to slow down indefinitely, their light growing redder and dimmer until they fade from view. Yet, from the astronaut's own frame of reference, they would be stretched and elongated in a surreal, inescapable descent. Beyond the event horizon, what lies inside? Once past the event horizon, reality becomes strange. The singularity at the center is hidden from the outside universe, but what actually happens inside? Some theories suggest that black holes could be gateways, wormholes to other regions of space or even other universes. Others propose that information falling into a black hole isn't destroyed, but encoded on the event horizon itself, a tantalizing hint at the deep connections between gravity and quantum mechanics. One of the most mind-bending ideas is the holographic principle, the possibility that the entire three-dimensional volume of a black hole is encoded on its two-dimensional surface. If true, this could redefine our understanding of the universe itself. Supermassive black holes and the cosmic tapestry. Not all black holes are born from dying stars. Some, known as supermassive black holes, sit at the hearts of galaxies, including our own Milky Way. These giants are millions or even billions of times the mass of our Sun, and their origins remain mysterious. They shape the evolution of galaxies, pulling stars into orbit around them, influencing cosmic structures on a grand scale. At the center of the Milky Way lies one such beast, Sagittarius A. Hidden behind clouds of interstellar gas, it is a silent sentinel, its presence revealed only by the swirling dance of nearby stars. In 2019, humanity saw the first-ever image of a black hole, a glowing ring of light surrounding the darkness of its event horizon. It was a historic moment, proof that these cosmic abysses are real. Escaping a black hole's grasp, Hawking radiation. For all their power, black holes may not be eternal. In the 1970s, physicist Stephen Hawking proposed a groundbreaking idea: black holes slowly evaporate. Through quantum effects at the event horizon, tiny particles of radiation, now called Hawking radiation, are emitted. Over unimaginable timescales, this radiation causes the black hole to lose mass, shrink, and eventually disappear. This means that even the most massive black holes have a lifespan, albeit one measured in trillions upon trillions of years. The final mystery. Black holes challenge our understanding of the universe at the deepest levels. They blur the lines between space and time, matter and energy, reality and illusion. They are cosmic paradoxes, where the very laws of physics break down. Perhaps in the distant future, we will unlock their secrets. Perhaps we will one day harness their power or even travel through them to other realms of the cosmos. For now, they remain as they have always been, silent, dark, and endlessly mysterious.